I'm going to walk you through the implementation of our mechanism in Julia, getting numerical results. You'll be able to get numerical results using this program that I wrote for the particular mechanism that we have been dealing with in this video series. So, since Julia might be new to maybe all of you actually, I'm going to briefly talk about how to install Julia, and then I'm going to describe this program that I wrote, and then we're going to use it to get solutions to position and velocity level um, kinematic problems, kinematic questions. Essentially, we're going to solve position level solve for the position level variables and the velocity level variables. Um, okay, so let's go through this. First of all, Julia. Okay, so to talk about Julia, we go to, to get our initially start with Julia, you go to julialang.org. Here, this is the Julia website. You can see that it's pretty simple actually to navigate through this. But in any case, to install Julia, you would go to download. And here you have a bunch of options to choose from when installing Julia. Now, Julia runs on Windows, Mac OS, and Linux. The operating system that I am using is Linux Ubuntu, and I strongly urge you to use either a Unix-based operating system. Unix-based operating systems are plenty, but one of them is Linux Ubuntu. There are other Linux distributions that you can use, like CentOS is a popular one. Also, important to note is macOS, Apple's operating system. It's also Unix-based. So Windows, I don't like as much. However, you can use Windows as well if you like. And I am not an expert in Windows at all. I have stopped using Windows a while ago, and now I kind of don't know how to use Windows anymore. But you can always go here, click Windows 64-bit binaries, and install Julia that way. You can see here, you can download it and install it. Now, since I'm using Linux, I actually opt for a different installation procedure. What I do is, instead of going here and downloading the Unix binary build for Julia, which you can click the 64-bit here, probably your computer 64-bit, and then install it using the binaries. What I do is I prefer going on GitHub. This is Julia's GitHub page, and I build Julia on my system locally by going through these instructions right here. Why am I doing that? Well, I am doing that because when you build Julia locally on your computer, then the builder, the C builder, has the opportunity to optimize Julia to your particular system. Now, your system has a certain CPU, has a certain random access memory, etc. And when you install a binary build, that binary build has been built on a different machine. That's not your system. That doesn't have the exact specifications of your system, and it's optimized for that machine. If you build your Julia yourself on your computer, then you'll get better performance. In any case, this also gives you the opportunity to learn about Git, which is a great version control system. To build Julia, essentially, you clone this repository from Git. This one, you clone it. You can either go here and download this as a zip file. What I do is I go here and clone this repository by copying and pasting this line to the terminal. So what I do is I go here and I go to here. I copy that. Sorry, I didn't copy it apparently. Control C. Go over here, Control paste. And then you can write here the directory that you would like to clone this Julia repository. So I have cloned this already. So I think in my apps folder, Julia.1.2.0 or something. That I've already done. So I'm not gonna do that, but I can go there. Um, and if I list the files in this folder, you can see I have a bunch of Julia, previous Julia versions installed here as well. I'm not using most of them. I can delete them, but they are listed here essentially. But that particular Julia, the most current Julia distribution, the stable release, is installed right here. Okay, and I did that by cloning it, and then I essentially checked out the current version, and then I ran make to build the Julia executable. So I ran make, and that built this Julia executable for me. Now, make, of course, essentially contains a bunch of commands that points the builder or C, C++, C, C++ builder where all the dependencies for Julia are. And then when you run make, essentially, it goes and builds the whole Julia on your system. Okay, so that's how you install Julia. If you don't want to deal with this, or you just try out Julia, you can just go again, as I mentioned before. You can, if you're using Windows, click here, or if you're using Linux, click here. If you're using macOS, click there to get the binary build. That's just going to install it like you're installing any other program. That you're going to get some performance hits, but probably not too important if you're just starting out with Julia. Then you can, if you want to get back that performance, you can do the source build as I have explained to you right now. Okay, that's very good. That's enough about Julia. You can see here there's a bunch of stuff here. The one thing that I'm usually like to show my students is that if you go here under the section Julia is fast, it says Julia was designed from the beginning for high performance. Click over there. You can see here how it compares to other languages. If I maximize this, so there's a bunch of benchmark functions here that were used on a bunch of different programming languages like C, Julia. You might be familiar with Rust, Fortran, Java, JavaScript. MATLAB is our famous program, Mathematica, Python, R, and Octave. And C is generally termed as the speed of light. Of course, that's a joke. Essentially, C is the baseline. The thing is that the belief is that Julia is as fast as it gets. Of course, it's not like a physical law. You can actually get better, faster. You can actually go faster than the speed of light, essentially the speed of C. And you can see that Julia here on the second column performs quite well on on any of these functions. Actually, it's very close to C. Actually, in Mandelbrot function, it is faster than C. But what you might compare Julia with, what you might want to compare Julia with is MATLAB. You can see MATLAB is all over the place. Similarly, Python over on the third to last column is all over the place. It's faster than MATLAB mostly, but definitely slower than Julia. And Julia indeed performs quite fast. So that's aside from being free, and that's the basic reason that I like to use Julia. Okay, enough about Julia. Enough about that advertisement. It's not like I'm getting paid by Julia, but essentially I'm trying to give you another option to use. Okay, so back to our program. Now, I can shut this command window down. Okay, so on the right hand side, I have the terminal. This is like Windows command line, but it's not Windows command line. This is what's called the bash in Julia. Sorry, not in Julia. In Linux, this is called the bash, and there's what's called the bash programming, which is very actually powerful. Anyway, so what I'm going to do is I'm going to go to my working directory where I keep the stuff about our course. um, and I am storing this mechanism file that I wrote in Julia in homework and under homework and Julia directory. So I go there. Here I have this mechanism.jl file that I'm going to go over, and I'm going to start Julia with the project pointing to the current directory. So this is the Julia REPL. Essentially, the REPL is where you type commands and get responses from Julia. Normally, in a C program, if you remember, there is no terminal or there is no REPL. You don't, uh, you know, it's not interactive. You run a C program, it runs and exits. Something was done, but you essentially need to, if you want to get the output, you write that output to a file or something. Here you can write 1 plus 2 and it will give you 3, just like in MATLAB actually. MATLAB has a REPL as well. I don't think it's called REPL, but I'm not sure about that. Anyway, this is Julia. I can do basic things here. So back to my program. So this program here, um, by the way, before I go to the program, this IDE that I'm using to write the program is Visual Studio Code. And I would recommend you to use Visual Studio Code. It's a pretty neat program. It handles, it gives you great power when you're writing programs. I like using Visual Studio Code. It's freely available. It's free for the community. Okay, back to the mechanism. So this mechanism.jl here that I wrote implements our mechanism. It finds numerical solutions to the loop equations and the derivatives of the loop equations, essentially, to give you, the unknown position variables and unknown velocity variables. How does this work? Let's look at it. Let's go line by line on this. Actually, before going line by line, let's execute it and see if it works. Okay, and of course I cheated. Of course I know it works. I wrote it and I tested it before making this video. So, but let me show you how it works at least. So what we do here is, the first thing we do is we go and create a mechanism, the mechanism. Essentially, I'm talking about a particular singular mechanism. That is the mechanism of problem 3.58 in our homework set number 3. Of course, I'm using this mechanism because it is the most complicated one of the most complicated problems in that set. Anyway, I create my mechanism and I get my first error. Okay, so the reason that this is complaining to me is that I have not let Julia know where the mechanism code lies. It is in this directory, but it doesn't know unless I tell it to include that file, mechanism.jl. So I need to first run this, which is going to go through the current directory, find mechanism.jl, and include it. Okay, so now it should know where the mechanism code is, and if I run my earlier code here, it's going to crunch through the numbers. The first time Julia runs, it's slow because it goes through your file and kind of compiles it. So right now I created a mechanism, but the second time I run this, if I want to create another mechanism, it's going to be lightning fast. You can see here I'm going to create another mechanism. It's lightning fast. Okay. Don't worry about this display. I didn't overload the display function, so when I create the mechanism, it displays a bunch of gibberish, or at least it looks like gibberish. It's not actually gibberish. Anyway, okay, so now I have defined my mechanism in the variable called m. Now I can say um, so I can say, so essentially, whenever I construct this mechanism, the mechanism object, it actually goes through the loop equations, solves it, and stores the solution in a field of the struct called Q. Q contains generalized positions. Essentially, Q is a vector that consists of theta 1, theta 2, theta 3, d4, and d5. So if I run my function get position on my mechanism object, I should get the solution, which is theta 1 here, theta 2 here, theta 3 here, d4 here, and d5 there. Of course, the angles are in radians, expressed in radians. So this is the solution you should have got in the other video series, in the other videos in the video series. Uh, so now what I can do here is I can say set position M and give it a new theta 2 value. Of course, the problem asked when the problem asked this question, it set theta 2 to be 135, but we can ask this code, what if theta 2 was say 100 degrees? Of course, I need to give it in radians, so I'm just going to convert it to radians before I send it to the program. I'm going to ask it to set the position theta 2 to 100. Of course, when I set the position to theta 2 to 100, theta 1, theta 3, d4, and d5 must change. It must crunch the numbers to modify theta 1 and theta 3, d4, d5 such that the loop equations hold. So let's run this. It gives this number. Don't worry about that number. That's the last element of the generalized position vector. But now, if I now do get position dot m, okay, so it gives me different numbers, thankfully. So these are essential. This is the theta 1 that corresponds to theta 2 equals 100 degrees. This is exactly theta 2. This should be 100 degrees. This is in radians. So 1.745 times 180 divided by pi is almost 100. Yeah, there we go. And these are the d4 and d5 values that correspond to this particular theta 2 value. And to check if this solution actually is a solution, is a solution to the loop equation, in other words, it satisfies the loop equation, I can run my loop equations function that I have created with this get position m vector and the current values of our link lengths. And I should get almost a zero vector, you see, because it's a numerical solution. And indeed, I get a vector that's almost zero. So great. So get position and set position works nicely and solves the loop equations to give me a solution to the unknown position variables. What about the velocities? Well, when I create the mechanism, I created it such that the code goes when the code goes through and actually solves for the velocity that was asked in the question. So if theta 2 in the question, theta 2 dot was 500 radians per second, and it was asking us what are the remaining velocities. And essentially, when I created the mechanism object here, it actually computed those, and I can ask them what are those velocities, ask the code what are those velocities, and indeed these should be the values that we got in the other video and the velocity level analysis video. Theta 1 dot is negative 95.4 radians per second, theta 3 dot is 120.6 or 7 radians per second, this is d4 dot, this is d5 dot. Very nice. Again, if I wrote a function that sets the velocity to some other theta 2 dot, say theta 2 dot is, what is it? Oh, by the way, this may not be exactly the answer we got because we changed the position. So I'm going to set the position back to what it was originally, 135. Oops. And then I should run the get position. Oh, that's fine. No, this is the solution. This is the solution because I have not set the velocity yet. If I ran set velocity m 500.0, it should change this because I've changed the state of the position variables essentially. Indeed, they have changed. Great. Okay. So if I go back to what the problem asked, right, the original problem asked, I must set my position to 135 degrees. And then I must set my velocity to 500 radians per second for theta 2, of course, theta 2 and theta 2 dot. Okay, and now I can inspect my velocities. And indeed, I have the solution that was included in the velocity level analysis video. Okay, very good. So it works as intended. Now, let's go through the code. How did this work? So here, the code I have written, I've written it in such a way that I avoided any global variables, the usage of any global variables. This is something that you should strive for when writing good code, okay? Where, be it a Julia code or be it C code, um, or I'm not actually sure about Fortran. I've never coded in Fortran, but I'm pretty sure about C and C++ and Julia, of course. Having global variables is bad. It is especially bad in Julia because, as I said earlier, when you run your Julia code, Julia first goes through your code, compiles it, and then the second time you run it, it runs lightning fast. The reason it runs lightning fast the second time is that when you first executed your code, it went through and determined the types of each variable. When I say type, what does it mean? It means whether a variable that I've defined is an integer, is it a float, is it a boolean, etc. It decided that, and then the second time you run it, it doesn't need to know them. It will remember it, and it will use those types to essentially increase the speed of computation. Of course, that's not the only reason it's fast, but it is one of the reasons. Okay, so why is global variables bad then? Because when you define global variables, Julia's interpreter will have no way of knowing what type that variable is going to be. Because when you have a global variable, you have the power at any time to change the type of that variable, and Julia will have to reinterpret the type of that variable every time you run your code, and it's going to be almost as slow as MATLAB because of that. However, if you avoid using global variables, or at least whenever you have defined a global variable, you define it as a constant, then Julia will know the type of every variable, because once you define those other variables and you write something differently, it's going to complain that you are changing the type of that variable. Essentially, uh, it's still going to run, but if you change the type of the variable inside your functions, but you're going to get a performance hit. So it's very important to write type stable Julia code, which what that means is if you define a variable to be a float of type float, say, that you keep that variable to have type float throughout your code, so that your code is type stable and Julia doesn't need to worry about you changing the type and getting a performance hit as a result. Okay, mouthful. Uh, Now, let's go through this code in which I define no global variables whatsoever, of course. And so I'm hoping that this is a clean written Julia code, even though there are some guys out there that knows how to write the code much better than me, than I do. But this is, I think, pretty clean. So here is our mechanism. It's a struct. This struct is like a Julia's version of a class. Julia doesn't have classes per se because it has something else called multiple dispatch, which is arguably more powerful than having classes. But either way, Julia gives you the opportunity to write structs, which were essentially classes um, before C++ came around. Anyway, so in this struct, I have some fields. This one field is A0. This is one of our constant lengths. A vector includes the other constant lengths, A1, A2, A3. Q includes our generalized positions, theta 1, theta 2, theta 3, D4, and D5. Q dot includes our generalized velocities, essentially theta 1 dot, theta 2 dot, theta 3 dot, D4 dot, and D5 dot. Q double dot or Q d dot is going to include my second derivatives of the generalized positions. I have not implemented the computation of accelerations yet. I will do it later. This F, DF, G, and DG, these are our essentially handles to our loop equations. One of them is for the four-variable loop equation. Essentially, I don't include theta 2 as a variable in the F, but I include it as a variable in G. And DF and DG are their derivatives. Okay. Here is the constructor for the mechanism class. The constructor takes some arguments. Well, some of the arguments are A0, A. These are the link lengths, remember. Theta 2 theta2 dot and theta2 double dot. Now, they have some default values. So when I call it over here m equals the mechanism with no arguments, it essentially, the program, what the program did is it went through this function, but called this function with these default values that I've set here. Okay, so those are the values that were given in the original problem statement, so I made them default values essentially. Okay, but if I wanted to create this mechanism with different link lengths, I could say, for example, A0 is 350 instead of 300, and the other link lengths are, I don't know, 370, 160, 170, and this would define. Of course, I didn't. When I say 350, it thought it's an integer, so I have to say it's a float. This will define another mechanism, the same mechanism actually, with different link lengths. This has defined a different mechanism. You know, the topology of the mechanism is the same, but only the link lengths have changed. Okay, so this gives us that opportunity when I write it this way. Anyway, let's suppose we defined our original mechanism that is defined in the question. Here I'm assigning some, essentially I need to construct q dot q double dot with the second variable equal to what are given to me. Here I'm saying this is my initial guess because I will use a numerical scheme to solve the position level loop equations like Newton-Raphson. Here I define my loop equation. This loop equation function is implemented below over here. I'll get to that. This computes the derivative of that loop equation using what's called an automatic differentiation scheme that is available in Julia. I don't think it is available in MATLAB, so that's a bummer because this is very useful and very convenient. You don't have to take the derivative by hand; it does that for you, and it does it in a very efficient fashion. I do the same thing, but with a 5-variable loop function rather than the 4-variable loop function. Then I solve the loop equations and I assign the solution, and then I solve the velocity level equations in matrix form, and then assign them to the q dot vector within the struct, and I create the struct right here using the new keyword. Okay, that's what happened. This is the constructor. All this thing gets executed when I write over here m equals the mechanism. At the moment I hit enter here, it executes all these things, okay, and gives me the mechanism object, and then I can look at what it contains, essentially what is my q vector, what is my q dot vector, what is my q double dot vector, then I can inspect them. Now this constructor used some auxiliary functions like loop equations. Let's go over them. This loop equations essentially are the loop equations that we constructed. Let's go back to that. If I go over here and then I go over there, you can see this thing over here. These are the loop equations, PL1 and PL2. Essentially, I wrote them over there literally by saying for D4 is, for example, X4, theta1 is X1, etc. By replacing them with X1, X2, X3, X4, X5, I wrote down the loop equations right here. This is what it uses when it creates this f function. And the reason I define another function f and not just use loop equations immediately is because the loop equations takes these extra variables as parameters, whereas my automatic differentiation will like me to not have more than 2 arguments of the function. So I'm defining another function by fixing those link lengths here. That's the only reason I defined another function there. Okay. Then the other function that I used was get position, set position, and get velocity and set velocity. Well, get position essentially just reports back what the struct contains in its Q field. So if I run get position, it just reports me what it contains in the Q vector. Essentially, we have solved for the loop equations and got theta1, theta3, d4, and d5. and collected them in a vector called Q, and it just reports me that back. When I do set position though, right? Set position, you call set position with a different value of theta 2 than what is given to us already. So when I write set position m with 120 degrees, let's say, of course it expects radians, say 120 degrees, let's say, it not only has to set theta 2, but it also has to go through the whole loop equation Newton-Raphson business to set the other variables to their correct values as well. Essentially, what is the theta 1 that corresponds to this value of theta 2? What is the theta 3 that corresponds to this value of theta 2, etc.? It has to solve them. So what happens when I hit enter here? Tick. Don't worry about this thing. This is the last this one here is the last element of the Q vector. So if I do get position, you see that this one is here is the last element of the Q vector, the new Q vector. What happens then? Well, I create another vector to store the values of the loop equations, and then what I call this is NL solve, nonlinear solve. Solve the loop equations again, right? With this guess. The guess is the current value of the position vector, generalized position vector. Using that guess, solve them, but the new value of theta 2. Once you solve them, assign that solution to the vector which is holding these generalized positions in this struct that we have just written. Okay, and then once that happens, of course, the Q vector, my Q vector got updated, and when I asked for the Q vector by using get position, it gave me new values, as you can see. Okay, so that's what set position does. Similarly, get velocity reports to me what the current velocity is r. Okay, but when I say set velocity and I specify some number here, say instead of 50, I can say that theta 2 dot is 55 radians per second. It's going to go through the velocity level analysis. Essentially, ax it will form those equations ax equals b that we discussed in class, solve them not only in the class but also in the videos, solve these equations and report back the velocities of theta 1, theta 3, d4, and d5. So essentially the rates of changes, not the velocities, but the rates of change of those variables. So I can then ask for get velocity, of course, and it will tell me these new numbers. Interestingly enough, this is pure luck. At 120 degrees with theta 2 dot equals 55 radians per second, theta 1 dot is 0, theta 3 dot is 0, and d5 dot is 0. That's literally amazing. I don't know how the heck I stumbled upon that. That's literally ridiculous. That's like as lucky as one gets. I should have bought a lottery ticket. Anyway, I will end this video here, and hopefully I'll make another video where I discuss doing the same thing in MATLAB.